Now, let's move further in the direction of nuclear physics, and we have to discuss in this video the liquid drop model of nucleus, and we would like to add some terms to this liquid drop model in the form of corrections, and finally we'll be able to achieve an equation known as Weizsäcker's formula. Now, uh, we have all is suggested by the title itself that what we are trying to do here is that we are making an assumption that a nucleus is like a liquid drop of water. So to say that what we have is the short range force that binds the nucleons so securely, so tightly. That's a short range force that we have between the nucleons, and by far this short range force that we have between the nucleons is the strongest known force of the nature. And this nuclear force, it's not well understood as electromagnetic force, and certainly the theory of nuclear structure is less complete. It's less complete, even though that it is less complete than that of the atomic structure, if so to say. And even without the full understanding of this nuclear force that we have between the nucleons, a lot of progress has been done by by developing nuclear models to account for the prominent aspects of the nuclear properties and the behavior of the nucleus. And to be precise here, what we have is the attractive force between these nucleons, and this attractive force is very strong. It's short range, and it is effective up to a very minimum separation of the order of 2 to 3 Fermi. The nuclear attraction between the two protons, it's about 100 times stronger than that of the electric repulsion that we have due to the protons which are present inside the nucleus. And we have discussed these things many a times when we talked about the properties of these nuclear forces. And the nuclear interaction that we have between protons and neutrons, and between neutrons, all of these interactions, as we have discussed, they appear to have same state of power. There's no difference between the force between neutron proton, proton proton, and neutron neutron. Now, if we assume that each nucleon in a nucleus as as an interacting particle, and is interacting with its neighbors. So we have a nucleon and it is interacting with its neighbors, and this situation it certainly does resemble with the situation of a solid, and it does certainly resemble with the situation of a liquid. And And if we talk about if we assume it to be a solid where we have particles identically vibrating at their main positions, the like of crystal lattice, or that or that of or that of the molecules that are vibrating in a liquid, and which is ideally which ought to be ideally free to move about while maintaining a fixed intermolecular distance. Now, the point arises here that if we make a comparison of nucleus with that of a solid, the calculations based on the vibrations of the nucleons about their average positions, it comes out to be too great, that the vibrations of nucleons that it's impossible for the nucleus to be stable. If we assume that we will treat this nucleus same as that of a solid, where we have fixed position of atoms, and these atoms or molecules, they are vibrating at their mean positions. So the results that we obtain by correlating the solid structure with that of a nucleus, it gives us freak results. And if we compare it with the liquid, on the other hand, it turns out to be extremely useful. So if we turn out assuming this nucleus resembles with that of a liquid drop, it certainly gives us it gives us extremely useful understanding of certain aspects of this nucleus. And this analogy was proposed by Gamow, and it was in detail developed by Weisesker. So to start here with the liquid rock model, what we assume is that the picture of a nucleus is, suppose it's a nucleus and it has nucleons in it. It's like a droplet of liquid, and this accounts for the observed variation of binding energy per nucleon with mass number. Now, what we assume here is that the energy associated with each nucleon-nucleon bond, if we have a nucleon and nucleon, there is a bond, assuming a bond between these two nucleons, and this energy is between nucleon. This energy is, say, for example, it is U. Now, this energy is actually negative since attractive forces are involved. We are talking about nuclear forces. So this energy that we have between the two nucleons in a nucleus, this is going to be negative, because whenever we have a bound system, the total energy of the system is negative. And but in this case that we are discussing right now, what we will assume that that choosing this U as positive, it's not, it can simply change the direction of physics, but it's not going to change the physics that we are going to get out of it. So the choice of taking this energy between the two nucleons here is positive. So this energy is assumed to be U. Now, if we talk about the bond, I mean, uh, we have the shared nucleons, and between the nucleons we have the energy. Now, each has a binding energy. If we talk about the binding energy of this system, the the binding energy between nucleon, that will be simply 1 by 2 of U. And when an assembly of spheres of the same size is packed around this nucleon into a smallest volume, so what we have is we have an inner nucleon, and this nucleon has the packing. It has the packing with its neighboring nucleons that are surrounding this nucleon. So if we assume that we have a nucleon inside the nucleus, it will have spheres of these nucleons surrounding the central nucleon. And what we assume here is the tightly packed assembly. We assume tightly packed assembly. So to say that if we assume that we have the tightly packed nucleons around this central nucleon, then each nucleon will have 12 spheres surrounding this nucleon. Hence, each interior nucleon in a nucleus has, so if I have to talk about each nucleon inside nucleus has binding energy equal to 12 times 1 by 2 of U, and that should give us 6U. So if I assume that we have the mass number, that means mass number gives us simply the number of nucleons. If I assume that the number of nucleons inside the nucleus is A, and they are all in the interior of the nucleus, assuming them all to be in the interior of nucleus, then I will say that the binding energy of the nucleus by the whole volume. So I will call that EV, binding energy of the nucleus due to the whole volume. That will be 6 times AU. So this is my binding energy for this whole volume. And I can introduce a constant here, and I will write EV is equal to some A1 times A. And A1 is the constant that's associated with this equation. I would like to call this as equation 1. So this energy that we have, this energy it's assumed to be persistent with all the nucleons inside the nucleus, and it gives us the volumetric or volume energy of the nucleus. And we can see that it is directly proportional to the mass number. And in some nucleons, if we talk about some nucleons on the surface, now what we have assumed is that every nucleon is inside the nucleus. So we have not taken into account. So you have a nucleon and you have a nucleon inside the nucleus. This nucleon, if we assume that it is closely packed with respect to its surrounding spheres, then this nucleon has an average energy of 6 times U. But in reality, we have nucleons on the surface, close to the surface. And when we have such a situation, so here what comes in action is that we don't have the same number of nucleons surrounding a nucleon on the surface of this nucleus. And the number of such nucleons it will certainly depend on the surface area of this nucleus. It is going to depend on that. And, and, and a nucleus of radius r, if I assume that I have a nucleus and it has a radius r, has an area. So what is its area? Its area is it's 4 pi r squared. And r can be chosen as or not a to the power of 1 by 3. So what I will have is I will have the surface area 4 pi r naught squared a to the power of 2 by 3. That should be the case. Hence, hence the number of nucleons that we have with fewer number of the nucleons surrounding them than the maximum number of nucleons that are surrounded by that surrounds a nucleon inside the circle. Sorry, inside the volume. This number is going to be less. That's for sure. And what we find is that the maximum number of bonds that we have for the nucleons who are on the surface of the nucleus, they are proportional to a to the power of 2 by 3. So should we using the surface energy term, and that surface energy term can be written as minus a2 a to the power of 2 by 3. So to say that what we have here is the negative energy we have, and this is called the surface energy of the nucleus, and it is important for the lighter nuclei, since a greater fraction of their nucleons are on the surface, because natural systems always tend to evolve under the configuration of they always try to evolve under the configuration of minimum potential energy. Always in that sort. And what nuclei does, they tend to be towards that configuration of maximum binding energy. Hence, a nucleus should exhibit the same surface tension effects as we think in terms of a liquid drop, where the molecules, say water molecules on the surface of a droplet, they don't have the resultant force acting on those molecules is not zero. But if we take a molecule at the center of this droplet, if we calculate the total force acting on this, it will come out to be zero. And about the molecules on the surface of the liquid drop, what they try to minimize the area, they try to minimize the energy. And in the absence of the other effects, it certainly should be spherical by virtue of this surface tension kind of thing that we have in case of nucleus. And since a sphere has least surface area for a given volume, so that's why we have in ideal conditions a liquid droplet. We don't have a cubical droplet of water. It's spherical because this shape is it basically favors the minimum surface area. Now the next term is the electrostatic term. Now we can think in terms of the protons that we have inside the nucleus. So P, and P. So certainly the energy that we will calculate in terms of these protons that energy will also be negative in nature. That's also gonna oppose the overall energy that we calculated in the very first case. So this electric repulsion between each pair of the protons that we have, it also contributes. It contributes towards the decreasing binding energy, and the Coulomb energy of the nucleus is the work that must be done to bring together two protons from infinity into some spherical aggregate. So the size of the nucleus, I mean, if we have to write down the potential energy of a pair of protons that we have. Now, if I have to do that, what am I going to write down is the potential energy and potential energy. And let's assume it is V. This V will be minus E square by 4 pi epsilon naught R. Now, what we have is that there are nearly Z times Z minus 1 by 2 pair of protons. That's clear. This much of protons. So this E Coulomb energy will be Z times Z minus 1 V by 2. And this is going to give me minus Z times Z minus 1 E squared by 8 pi epsilon naught 1 by R average. So this 1 by R average is the value of 1 by R that we have in the original equation. But this value has been averaged over all the proton pairs that are present inside the nucleus. And what is found is that if the protons are uniformly distributed throughout the nucleus of radius R, then this 1 by R average, is proportional to the radius of the nucleus. And hence, it is proportional to 1 by a to the power of 1 by 3. That should be the case. So in that case, what I'll have is I will have the Coulomb term that will be minus A3 times Z minus 1 by A to the power of 1 by 3. So this energy is also going to oppose the attractive force that the attractive energy that we calculated in terms of the volume of this nucleus. And this Coulomb energy is negative, and certainly it's a result of it's the result of the opposition that's out there in the nucleus between these protons. Now, this is a safe argument, as liquid drop model itself can move up to here. And to sum up these three equations, we have EV and we have ES, and we have what we have is EC. And what will be the binding energy of the nucleus? We will have EV plus E and S, plus we will have E Coulomb. Now we can substitute all of those values that we have, and we can obtain the relation. So what will be binding energy that we will have? It will be A1 times A minus A2 times A to the power of 2 by 3 minus A3 times Z minus 1 by A to the power of 1 by 3. Now, if I divide this equation by by A. So I'll get binding energy per nucleon. So that will come out to be A1 minus A2. Then what I will have is uh, A to the power of minus 1 by 3, then minus A3, Z times Z minus 1, uh, A to the power of minus 4 by 3. So this equation gives me the binding energy per nucleon. And and the matter of the fact is that this is a very good approximation. And if I have to um, uh, each of the terms that we have in this equation, if we plot them roughly together and sum up the binding energy per nucleons, and choosing the coefficients A1 and A2 and A3 based on some empirical binding energy per nucleon curve. The fact that the theoretical curves, if we see that what comes out here is something we have, if I have an axis like this, and if this is the state of mass numbers, we have this as volume energy. So this is EV per nucleon. and and then the other two energies, the one is Coulomb energy. Okay, that will be the behavior of Coulomb energy is something like this. And then we will have surface energy, and the behavior of surface energy is something like this. Both are negative, and we can choose some empirical. We will take a reference axis here as binding energy per nucleon. And what's the result of all the three curves is something like this. And the curve that I have shown here, it has a very good resemblance to what was predicted in binding energy per nucleon. And the fact that the theoretical curve that can be made to agree so well with this empirical one, it certainly means that there is the analogy between a nucleus and a liquid drop has at least some state of credibility that to some extent it can carry the nature of the binding energy per nucleon with the original values, with the values that are predicted. Now, this is what liquid drop could. This is all that liquid drop model could give us in terms of binding energy per nucleon, and what was added to this equation is simply called as correction. It's the correction to the formula. So this binding energy per nucleon that we have here, it can be improved further by taking into account two important effects. And these two effects, they do not fit into the sample of a liquid drop model, but which makes sense in terms of the model that provides for the nuclear energy levels. So now the correction terms that we are going to add to this equation, they are not a part of the liquid drop model. Now, what we are coming up here is we are coming up with an assumption that nucleus has energy levels. So to speak here regarding this is that some of the effects, I mean, when neutrons in the nucleus, when they outnumber the protons, that means that the higher energy levels have to be occupied than that of the protons. In inducing the idea of energy levels into the nucleus, there is addition of some correction terms to the liquid drop model. Now, if we assume that the uppermost neutron and proton, if I take a simple schematic diagram over here, what is important here is that we can have pairing of neutrons and protons in these energy levels. If we think of energy levels here in a nucleus, and uh, and certainly there is a limit to filling of the particles in these energy levels, and this limit is given by Pauli's exclusion principle, and it certainly limits two particles uh, and which have the same spacing between the two energy levels, assuming that spacing to be E and to be E. Now, in order to produce a neutron axis, because what we are trying to do here is that we are trying to understand that if we have axis of neutrons in the nucleus, what's going to happen? What kind of negativity will evolve in the nucleus? So that's the intuition that we are trying to explain using this diagram. Now, to produce a neutron axis, say, for example, as quoted by many of the authors, let's take it, this n minus z is equal to 8. And we are not changing, we are not changing the mass number, not changing the mass number. So mass number is same. And then what we will have is we will have 1 by 2 times n minus z, and this will give us 4 neutrons. This is going to give us 4 neutrons. And these 4 neutrons, what they will have to do is and become neutrons to the next energy levels. If that energy is, say, delta E, that energy comes out to be 1 by 2 of n minus z times 1 by 2 of n minus z of E by 2. Okay, so simply multiplying the number of the neutrons that we have created in the upper energy levels by the change, by the energy that they will have, that will give us the rise in energy, the energy that's supplied to the system. So if I choose here, so what's going to be here is it is 2, 4, 8. This is 1 by 8. Probably it is 8 E by 8 times n minus z whole square. So this is the energy. Okay. So moving on from here, what we will have is we will have, because I understand that this number of neutrons is A minus Z. Okay, so what does that mean? That means n minus z that I have whole square in the above equation, it is simply A minus 2z whole square. So what I will have delta E equals, it equals E by 8 times A minus 2z whole square. Now, this is the energy that might be supplied to the protons to go into that next higher energy levels, and this energy is going to be, this energy is going to increase with the increase of number of nucleons in the nucleus, and the smaller is the energy level spacing with E proportional to the mass number. So for big nucleuses, the mass number is large, so the the spacing between the energy levels that we assume here, that spacing is going to decrease. But for the nuclei whose mass number is small, the spacing between the energy level is going to increase. And this means that there is asymmetry, and there is an energy, what's called as asymmetry energy. Asymmetry energy. And this energy, if I choose equal to EA, which is calculated, due to the difference between the number of neutrons and number of protons. So this asymmetry comes in action when we think of having more neutrons in a nucleus than the number of protons. And this gives rise to the energy known as asymmetry energy, which we have analytically, which we have calculated as minus delta E. So this is going to be minus A4, A minus 2Z whole square. That is the energy due to asymmetry, having different number of neutrons and protons. So when the number of neutrons and protons is same, then you can't think of the energy due to asymmetry here in this case. So now if the number of neutrons is large, it certainly gives rise to asymmetrical energy. And that is that's given by minus A4, A minus 2Z the whole square. Now after this, what we have is the last correction. And this correction comes from the tendency of pairs. So you have pairs of protons, and you have pairs of neutrons and neutrons. So protons, neutrons, or protons, neutrons. Now, if we have even nuclei, and even nuclei are the most stable, even nuclei, they are most stable and hence have higher binding energy than would have been otherwise. Okay, so if we have even nuclei, then the binding energies are extremely large. And the examples of such nuclei are helium 4 and 2, and oxygen 16 and 8. So what they have is even number of neutrons, and they have even number of neutrons and protons. So to speak from here is that at the other extreme end, if we have odd nuclei, so having odd nuclei, they certainly have they both have unpaired protons and neutrons. So they have one proton and one neutron, and have relatively low binding energies. They have very low binding energies because their outermost protons and neutrons are not, their octet is not complete. They are singly out there in these shells. And the pairing energy that we are talking about, it is positive. This energy is positive for even nucleus, and this energy is negative for odd nucleuses. And it seems to vary with mass number as in the power of A to the power of minus 3/4. So finally, what we have is we have E pairing, the energy that comes by virtue of pairing. So plus for even nuclei, minus for odd nuclei, and we have 0 for even odd nuclei, and we have a constant, and we have the dependence on a to the power of 3 by 4. And uh, and this will give me the energy due to the pairing that we have inside the nucleus between neutrons and protons. So to say is that if we combine now all the energies that we have, what we have is we have volume energy, then we have surface energy, then we have Coulomb energy, uh, then we have asymmetrical energy, then we have pairing energy. Combining all these energies gives us the expression simply known, and this expression was basically obtained by this man named C.F. von Weizsäcker. So this man developed it, and that's why this semi-empirical binding energy formula is also called as Weizsäcker's semi-empirical formula. So what will be that? That will be the binding energy of the nucleus is A1A, this is the first term, minus A2A to the power of 2 by 3, this is the second term. This is due to the surface of the liquid, then minus A3 Z times Z minus 1 by A to the power of 1 by 3. This is due to Coulomb force. Then we have minus A4. This is due to what we call as asymmetry, in formulation of neutrons and protons in the energy levels. That is A minus 2Z whole square by A. Then we have the last term, that is plus, minus, and 0. What is that? That is A5 by A to the power of 3 by 4. So this will give us, this gives us the semi-empirical binding energy formula, and this formula is also known as Weizsäcker's formula. And taking into account the permissible values of these coefficients that we have in every term in this equation, the result obtained by this equation is a very good approximation, even though it does not explain most of the properties, but it's a very good approximation to understand the binding energy curve of the nucleuses.